Let's now walk through an example of a mass spring system with no damping. A 24-pound weight, represented by this mass in our blue box, stretches a spring 4 inches. The mass is released from a point 3 inches to the right of the equilibrium position, and it has an initial velocity of √6 feet per second. In this system that we're looking at, there is no damping. We're going to let x of t represent the displacement from equilibrium, and that's going to be measured in feet. We are asked to find the equation of motion and then determine the amplitude, angular frequency, period, and frequency. Notice in our diagram that our spring is stretched to the right of the equilibrium position, and that equilibrium position is given as x is equal to 0. We're going to start by writing down the equation for free undamped motion. That equation is m d squared x dt squared, that's just the acceleration of the mass, plus k times x, that's due to the spring, and that's equal to 0. The initial position, x of 0, is equal to 3 inches because it's released from rest 3 inches to the right of the equilibrium position. And then dx dt at time 0, that's just the initial velocity, and that is √6 feet per second. In step 2, we are going to find m and k. Let's find m first. To find m, we have to use the formula that weight is equal to mass times gravity. So that tells us that mass is weight divided by gravity. We're told that the weight is 24 pounds. So we'll put in 24 pounds. And then we're going to divide by gravity. Because we have pounds, we have to let g be equal to 32 feet per second, and this is equal to 3/4, and this is often called slugs, instead of pounds times seconds divided by feet. Now let's find k. K is the spring constant, and Hooke's law tells us that the absolute value of the force is equal to k times d, and that is equal to the weight of the mass. Solving for k, we get that it is equal to w divided by d. Our weight is 24 pounds. And then d is the amount that the spring is stretched, and we're told that our spring was stretched 4 inches. So we're going to put 4 inches here. And since gravity is in terms of feet per second, we're going to change inches to feet. So we just have to multiply by 12 inches and divide by 1 foot. 4 goes into 12 3 times. So we end up with 72 pounds per foot. I'm going to go ahead and highlight these because we're going to need them in just a second. What we have to do now is solve the equation. Let's begin by substituting the values that we just found for m and k into our equation. This gives us 3/4 d squared x dt squared plus k, which is 72, times x is equal to 0. Let's multiply everything by 4 and divide by 3, and that gives us d squared x dt squared plus 96x is equal to 0. This is a second order constant coefficient differential equation, so we can assume that our solution is x is equal to e to the rt. Substituting this in, we get r squared e to the rt. The r squared just comes from the two derivatives. And then we have a 96 e to the rt is equal to 0. We can factor out r squared plus 96 times e to the rt. An exponent can never be equal to 0, so we are forced to set r squared plus 96 equal to 0. Let's come over here. This gives us r squared is equal to minus 96. So r is plus or minus the square root of minus 96. This is plus or minus the square root of minus, let's write this as 16 times 6. So this gives us plus or minus 4 times root 6i. Since we have a complex root, we can write our equation of motion as x of t is equal to c1 cosine 4 root 6t plus c2 sine 4 root 6 times t. Let's now take this over to our next page because we're running out of space. What we need to do now is find c1 and c2, and we're going to use our initial conditions to do that. We were told that x at 0 is equal to 3 inches. I am going to change this to 1/4 of a foot, so our units match up. And we're told that dx dt at time 0 is equal to root 6 feet per second. Let's first substitute in that t is equal to 0. Cosine of 0 is 1, so this just gives us c1. Sine of 0 is 0, so we know that c1 is 1/4. Now let's find dx dt. We'll wait for a minute to plug in 0. This gives us minus c1 times 4 root 6, that comes from the chain rule, times sine 4 root 6t, plus c2 times another 4 root 6 times cosine 4 root 6t. Now we can plug in that t is equal to 0. Sine of 0 is 0, so that goes away. Cosine of 0 is 1, so we have 4 root 6 times c2, and we're going to set that equal to our initial velocity, which is square root of 6. From this, we get that c2 is equal to 1/4. Here's our c1, and there's our c2. Let's plug them back now into x of t. So we get x of t is c1, which is 1/4 cosine 4 root 6t, plus c2, which is 1/4 sine 4 root 6t. And there's our solution. In our last step, we need to find the amplitude, angular frequency, period, and frequency. In order to do this, we are going to need to write our solution in a different form. Our solution is written in this form. X of t is equal to c1 cosine omega t. I'm just writing the general form here, plus c2 sine omega t. We need to write it like this. We need to write it as x of t is equal to a, which is the maximum displacement from equilibrium, times cosine omega t minus phi. And phi is called our phase constant. Let's write down the general formulas first. Our amplitude A is the square root of c1 squared plus c2 squared. And then phi is equal to the inverse tangent of c2 divided by c1. Let's now plug in our constants. Our amplitude is the square root of c1 squared, so we have 1/4 squared, so that's 1 over 16. And then same thing for c2 squared. This is then equal to the square root of 2 over 4. Now let's do our phase constant. We're going to have the inverse tan of c2, which is 1/4, divided by C1, which is 1/4. So this is the inverse tan of 1. And this is equal to pi over 4. Let's now substitute these back in. Our amplitude is the square root of 2 over 4, and our phase constant is pi over 4. We can now write x of t as root 2 divided by 4 times cosine of omega, which is 4 root 6 times t minus phi, which is pi over 4. Now that we have x rewritten in this new form, we can find these four quantities. The amplitude is equal to a, and it's just the constant that multiplies our trig function, and that is the square root of 2 divided by 4, and the units for that are feet. The next is the angular frequency. That is equal to omega, and we already found that omega is 4 root 6, but now we need to add units, and those units are going to be radians per second. Now let's find the period. That is represented by the capital letter T, and it is equal to 2 pi divided by omega. So this is 2 pi, all divided by 4 root 6. The 2 can cancel out, and this gives us pi divided by 2 root 6, and the units are going to be seconds. Now we only have one more, and that is the frequency. That is little f, and it's just equal to 1 divided by the period. So this is 2 root 6 over pi inverse seconds, and this is often written as 2 root 6 over pi hertz. Now let's look at the graph of x of t so that we can see how the mass is moving. This coordinate is x, and this coordinate is t. When x is equal to 0, it is at the equilibrium position, and that occurs at this time, this time, this time, this time, and that pattern continues. What we have is simple harmonic motion, and the oscillations are going to continue indefinitely. When the value of x is positive, the mass is moving toward the right. Notice that the mass starts out at 0.25, which makes sense because it started out being displaced 1/4 of a foot, and then it had an initial velocity. So instead of moving back toward the left and x decreasing for just a little bit, it moves further to the right, and then the force of the spring pulls it back towards the left. And it moves to the equilibrium position, and then it goes left of the equilibrium position, and then it starts to come back to the equilibrium position. The maximum amplitude stays the same because there is no damping force. In the next video in this series, we're going to have a damping force, and we'll see what happens to the amplitude. And that's it. You now know how to model and solve free, undamped mass spring systems. You should now be ready to work through a problem like this on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.